Welcome to NASA STEM EPDC Quick Bits Science and Engineering Practices. NASA STEM Engagement and Educator Professional Development Collaborative provides NASA resources and STEM strategies for STEM engagement. In this series, we intend to reach educators, parents, and caregivers to quickly explain a specific big idea in STEM. We will introduce a NASA example of how this idea is applied in the real world, and finally, we will demonstrate step-by-step how to lead this activity at home or in the classroom with your students. You might invite your students to watch with you at that time. We invite you to join us as we learn more from our specialists. Let's get started.
Hi, I'm Dr. Samuel Garcia, NASA Education Specialist at Kennedy Space Center in Florida. The title of this activity is Triangulating Your Flight. This Quick Bits big idea is to present science and engineering practices when using math and computational thinking. That is, organizing simple data sets in order to reveal the patterns that show the relationships among variables. Describing, measuring, and/or calculating quantities such as area, volume, weight, and time. Applying math concepts and/or calculations such as ratio, rate, percentage, basic operations, and simple algebra to solve scientific and engineering questions and problems. Developing and/or using graphics and/or tables generated with simple algorithms to compare alternative solutions to an engineering problem, and using math representations to describe and/or support the scientific conclusions and the design solutions. Aeronautics is one of NASA's next-gen STEM programs. It focuses on the research and technological developments in aeronautics that have served as small steps and have been an important part of many significant NASA accomplishments known as giant leaps. Aeronautics focuses on the latest in aeronautics and the principles of sound, especially on research to create a new generation of experimental aircraft. We will focus on the activity called 3, 2, 1, Takeoff, complex version. The objectives of this activity are to explore geometry and its relationships to the design of airplanes, to explain to students the forces of flight and how important they are to understanding how NASA uses these principles when designing an airplane. In this activity, students will build a small paper X-plane and fly it by producing its own thrust, by blowing through a straw, and at the same time they will examine Newton's third law, the law of motion. The students will design and build a second plane, trying to improve the previous design, and they will try to fly it at a greater distance. But how is it that airplanes of any size and weight are capable of taking off and staying balanced in the air? My hypothesis is that the wing design and the fuselage are important. That is, the measurements and shape in which they are designed. Even with today's technology, NASA uses the same aeronautic principles used by the Wright brothers in 1903. And to understand these principles, it is important to understand the four forces of flight, which are drag, thrust, lift, and weight, which must be balanced for an airplane to maintain its stable flight, as well as Newton's third law of motion. Aeronautics is the study of the science of flight. Aeronautics is very important at NASA. The first A in NASA stands for aeronautics. NASA's aeronautical engineers must understand four basic areas to design an airplane. Aerodynamics, which helps the engineers design the geometric shape of the plane, including the wings. Propulsion, which will help engineers determine the type of engine and the appropriate amount of force that an airplane needs. The materials and structure, and the stability and control that engineers will study to control speed, direction, and altitude. The geometry of the wings is one of the main factors affecting the lift of the airplane. The airflow, which moves faster over the top than on the bottom, results in a low pressure that is located at the top of the wing, which makes the wing and the airplane attached to it fly. Some of the factors affecting the lift are the geometric shape and size, the airflow velocity and inclination, mass, and viscosity. Then, my hypothesis may be correct. Remember that in both science and engineering, math and computer science are crucial tools to represent physical variables and their relationships. For example, to obtain the exact or approximate solution to equations and to determine and apply quantitative relationships. Mathematical and computational approaches allow scientists and engineers to predict the system behavior and verify the validity of such predictions. To analyze whether the hypothesis of wings geometry affecting the airplane's flight was correct, I invite you to do the activity 3, 2, 1 Takeoff complex version. You'll need a guide to the activity 3, 2, 1 Takeoff complex version. The materials for the activity are the plane template, adhesive tape, scissors, ruler, measuring tape, pencil, and the straw. I used a biodegradable straw. You'll take the X-plane template located on page 3 of the Activity 321 Takeoff Complex version, which you will cut, and you'll put aside the optional part for design number 2. You'll cut the wings and the fuselage, or airplane body, which is a small rectangle. Once completed, you'll have 2 parts. You'll take your pencil and the rectangular part, or fuselage, and you'll wrap it around the pencil. Take some adhesive tape and join your airplane fuselage, being careful not to stick it to the pencil. That is, avoid the tape touching the pencil. The pencil should slide easily. Then, join the paper airplane wings to the fuselage using adhesive tape, being careful not to join this part to the pencil. Next, take the fuselage tip, twist it a little bit, and use some adhesive tape to seal it better. Remember that to make this airplane fly, you will need to produce one of the 4 forces of flight called thrust. That is why it is important that the plane is sealed as much as possible. The next step is taking the pencil out and placing the straw in its place. That's it. Your X-59 model will be complete. Now, let's try it. As a first step for this design, you'll have to measure the length of your plane in centimeters and draw the shape of its wings. Write down this information on your data table. Now you're ready. Let's fly it. 3, 2, 1, take off. Don't forget to write down the information about your 3 trials and the average distance, which is obtained by summing up the 3 distances of each trial and dividing the results into 3. Then, it's time to make your second design. In my case, I modified the wing geometry of my plane. Remember to modify only one variable at a time. And the design that covered a greater distance was my second design, with an average distance of 2.067 meters. NASA's aeronautics innovators are experimenting with a new wing design that removes the pitching and increases the airplane efficiency by reducing its resistance. In addition, they experiment with models where the airplane wings and tail could be joined following the same line, and they would use composite materials for their structures. Here's some discussion questions. I hope this activity was to your liking. 3, 2, 1. Let's have some fun while learning. See you soon.
Thanks for watching this NASA STEM EPDC Quick Bit. Don't forget to check out the description below for more information and links.